I also want to thank the organizers for giving me the opportunity to present at this conference. The title of my talk is Ordering Awad-Tsallis Quantile Entropy and Applications to some Stochastic Models. Here is the outline of my presentation. There are many generalizations of Shannon entropy. For example, Tsallis entropy, Kaniadakis entropy, Renyi entropy, Varma entropy, etc. With applications in areas like physics, communication theory, probability statistics, and so on. Tsallis considered another formula in Shannon entropy instead of classical logarithm, obtaining in this way Tsallis entropy. With this entropy, we obtain many applications, especially in physics. Awad also generalized Shannon entropy, defining Awad-Shannon entropy. Awad-Shannon entropy has some advantages, some of them being this entropy is always positive or non-negative, let's say like this. Awad-Shannon entropy of a continuous random variable is a natural generalization of Awad-Shannon entropy of a discrete random variable, and two different systems will have different Awad-Shannon entropies. By using the ideas of Awad, we can generalize some of the above mentioned entropies. We make this for Tsallis entropy, defining Awad-Tsallis entropy. For Awad-Tsallis residual entropy, we define a stochastic order, study the closure and reverse closure properties of this order, of course, and prove the preservation of it in some stochastic models like the proportional hazard rate model, proportional reversed hazard rate model, proportional odds model, and record values model. Here is the definition of Tsallis logarithm. This is another formula from here considered by Tsallis. It is called logarithm, like the classical logarithm, but Tsallis logarithm by many authors. In this note, we assume that alpha is positive, alpha being this parameter. For any absolutely continuous and non-negative random variable x, we use classical notations, namely the distribution function is denoted by capital Fx, the survival function by bar capital Fx, and the probability density function by Fx, small fx. We consider this supremum, which appears in the definition of Awad-Shannon entropy, and assume that it is positive, it is not zero, and is finite for any density function which appear here. Awad-Tsallis residual entropy is defining like this. We have here this supremum. And we recall the definition of the quantile function of the random variable x. It is here. In the literature, there are papers in which the authors consider quantile versions of Shannon residual entropy, of Renyi residual entropy, of Varma residual entropy, and of Awad-Varma residual entropy. For Shannon and Renyi, of course, there are many papers, not only those from here. In this work, we continue to develop that for a quantile version of Awad-Tsallis residual entropy by defining this function c x at. X is the random variable, at Awad-Tsallis. C, which is defined like this. We have h here and qx below. Okay, after some computations, we have these formulas for C. We remark the appearance of Tsallis logarithm in all formulas because we work with Tsallis entropy, more exactly Awad-Tsallis entropy, because of this delta x. If we remove this delta x, we obtain only Tsallis entropy, of course residual, Tsallis residual entropy, without this delta x. For another absolutely continuous non-negative random vector y, we use the same notation, capital F, y, etc. And for another random variable z, the same notation. We say that the random variable x is smaller than the random variable y in Awad-Tsallis Quantile Entropy order and denote like this if we have this inequality. The main result of this presentation is the following, namely, x is smaller than y in Awad-Tsallis Quantile Entropy order if and only if this conditional expectation is non-negative for any non-negative t. In the next slides, we want to show that the dispersive order and the convex transform order will imply Awad-Tsallis Quantile Entropy order. We have the definitions of the dispersive order and of the convex transform order, and the next two theorems say that if x is smaller than y in the dispersive order, then x is smaller than y in Awad-Tsallis Quantile Entropy order. Of course, we have some condition for delta x and delta y for the supremums considered above. Respectively, for the convex transform order, if x is smaller than y in the convex transform order, then x is smaller than y in Awad-Tsallis Quantile Entropy order. Of course, again, some conditions. In the fourth section, we are concerned with the closure and reverse closure properties of the introduced order, namely Awad-Tsallis Quantile Entropy order, under some transforms like parallel and series operation. For this, let us consider a finite number x1, x2, xn, and y1, y2, yn of independent and identically distributed copies of x, respectively of y. We also consider the minimum and maximum random variables x1n, y1n, the minimum, and xnn, ynn, the maximum. And we have the following two theorems. More exactly, if x is smaller than y in Awad-Tsallis Quantile Entropy order, then xnn is smaller than ynn in Awad-Tsallis Quantile Entropy order. Respectively, if x1n is smaller than y1n in Awad-Tsallis Quantile Entropy order, then x is smaller than y in Awad-Tsallis Quantile Entropy order. Again, we have some conditions for this supremum. The natural generalization of this is to consider, instead of a finite number n, a positive integer random variable capital N, like this. x1n, where n is a positive integer valued random variable. To this end, we consider two sequences of independent and identically distributed copies of x and y respectively, and n to be a positive integer valued random variable such that n is independent of xi and xi's and yi's. We consider the minimum and the maximum random variables like above, but instead of a finite number n, we have here capital N, a positive integer valued random variable, and we want to have the same theorems like above, and we have them. If x is smaller than y in Awad-Tsallis Quantile Entropy order, then x and n is smaller than y and n in Awad-Tsallis Quantile Entropy order. The same thing for the minimum, like above, of course. In the fifth section, we investigate the preservation of this introduced order in some stochastic models. We begin with the proportional hazard rate model, which is defined here. More exactly, x of theta and y of theta for theta positive are two absolutely continuous non-negative random variables given by the survival functions f bar x at power theta and f bar y at power theta respectively. And we have this theorem which says that depending on theta, we have x is smaller than y in Awad-Tsallis Quantile Entropy order. Then if x is smaller than y in Awad-Tsallis Quantile Entropy order, then x of theta is smaller than y in Awad-Tsallis Quantile Entropy order. And in another case, theta being greater than 1, if x of theta is smaller than y of theta in Awad-Tsallis Quantile Entropy order, then x is smaller than y in Awad-Tsallis Quantile Entropy order. Of course, again, we have some conditions for the supremums. For the proportional reverse hazard rate model, which is defined here, we have something similar, but not identical, because here we have theta between 0 and 1, and now we have theta greater than 1. And we have this theorem for the proportional reverse hazard rate model. It's practically the same thing. X is smaller than y in Awad-Tsallis Quantile Entropy order implies x of theta is smaller than y of theta in Awad-Tsallis Quantile Entropy order. Something analog for theta between 0 and 1. We apply this theory to proportional odds model, which is defined like this. Xp and Yp are the random variables having these survival functions, and we have something similar like in the above models. Finally, for the record values model, we obtain practically something similar, but this model is defined here. Rnx are the nth record values, Rnx, and Rny, and we have the following theorem. If x is smaller than y in Awad-Tsallis Quantile Entropy order, then Rnx is smaller than Rny in Awad-Tsallis Quantile Entropy order. N is greater than 1 being a natural number, a positive integer number. And we have another point here, namely, if n is strictly greater than m, being positive integer numbers, and if Rmx is smaller than Rmy in Awad-Tsallis Quantile Entropy order, then Rnx is smaller than Rny in Awad-Tsallis Quantile Entropy order. In all theorems, in all 4 theorems, we have some conditions for the supremum: delta x, delta y, delta x theta, delta y theta, delta r, n x, r, n y, etc. And we have some references, some selected references for this work.
Okay.
And thank you for your attention.
Thank you. Thanks a lot. Congratulations on great presentation, on great paper. Any questions? We have, I think, 5 minutes, so quite enough time. Thank you, Razvan. Very interesting. I will start with some of mine. So firstly, I do not know exactly in particular on quantum entropy models naturally, but the relationship that you have between two random variables in terms of ordering in Awad-Tsallis preference ordering, what are its properties? Is it monotone? Could there be some problems also in the ordering related to Awad-Tsallis, this whether x is lower or equal than y in Awad-Tsallis quantile order? And also, I did not understand this quite clearly. What does Awad-Tsallis quantile entropy add, or when do you use it compared to other quantile entropy ordering? Say, why are the models that you presented, proportional hazard, record, and so on, preferable for this type of quantum entropy modeling? I hope.
Yes, yes,
Thanks.
thank you. for first question, in many areas, I didn't work on something more applied, but I know that there is very important, especially for Shannon, because it is more studied for Shannon entropy and for Awad Shannon. Afterwards, for Tsallis and so on, it is more important to compare to random variables. I didn't work on it. I didn't read much, but I know that it is important, and I work on some theoretical. What Tsallis for the second? What Tsallis entropy? Why Tsallis entropy is used? Again, we arrive in some applied things. But in physics, there are many phenomena which can be modeled by Tsallis and not by Shannon. This is why Tsallis introduced this entropy. For Awad, it is better to work with it because it is positive. Awad Shannon, Awad-Tsallis, and in Shannon we don't have non-negativity. Positive, I use it in the strictly sense, but for Awad we have the non-negativity. For Varma, for another entropies, Varma offers two parameters instead of Tsallis, which works only with alpha, and Varma have two parameters which gives more flexibility in some theorems applications. But to summing up to the second question, these entropies, Tsallis, Reni, Varma, Kaniadakis, are especially applied in physics in some phenomena which can be modeled by Shannon entropy.